Hello everyone, myself Lijike, a postgraduate student in Embedded System Technologies from Weltech University. My project is on software defined radio with Ethernet interface. I am guided by Dr. P. Chandrasekhar, PhD, an associate professor and head of the department of EEE. I am externally guided by Mr. Saket Manukonda, a scientist from Samir, CEM. Abstract. My project aims to control RF transceivers remotely. To control some transceivers or transmitters, some parameters like frequency, modulation, power levels, data rate, sync word, etc. have to be initialized. There are two methods for parameter setting, local method and remote method. Local method includes setting of parameters manually using knobs and switches on the transmitter itself. Remote method uses computers and other communication means to control and set the parameters without using knobs and other systems. Our project aims in developing a GUI using LabVIEW to set parameters for transmitter initialization. Our radio nodes are ADF7020 transceivers which are controlled by PIC microcontrollers. This LabVIEW based GUI acts as a client and radio nodes together with the Raspberry Pi acts as server. Existing technology. GUI is used to access Ethernet using a Spark, Java, Red Hat, and local control of RF transmitters is done by manual adjustment of parameters using knobs and LCD display. Next is proposed technology. There are two radio nodes which are controlled using GUI developed in the LabVIEW. The client part is realized using LabVIEW GUI, which is interfaced with the PIC node using Ethernet cable. Ethernet interface with the PIC is done with the Raspberry Pi board. The two parameters like frequency and power levels of transceivers can be adjusted using this LabVIEW GUI. Ethernet interface uses TCP communication protocol, and the Raspberry Pi sends the parameters and a message to the transmitter section through USB port. Serial port in the PIC transmitter node receives the data and transmits a message in adjusted frequency and power level. Receiver part operated with the corresponding transmitter frequency will receive the data. Power level can be verified by measuring the range of transmitter and receiver. The higher the power level, the greater the range will be. Hardware is required. A PC to create a GUI using LabVIEW, and also for MBLab installation and programming of PIC microcontroller. Raspberry Pi board is to realize Ethernet interface between the GUI and the PIC microcontroller based radio nodes, and this can also be used to have a serial communication between the Raspberry Pi and the PIC microcontroller board. PIC microcontroller is used to program and control the ADF7020 transceiver, which is an RF module. ADF7020 is an RF transceiver which works with 430 megahertz frequency up to 930 megahertz, and the data rate is 200 kilobits per second. It has a power level of minus 16 dBm to plus 13 dBm. Softwares required are LabVIEW 8.5 to create a GUI, embedded Linux to program Raspberry Pi. And there are two codings we have to done in the Raspberry Pi. For one is a server coding, and another one is serial communication using USB port, and the interfacing that with the PIC microcontroller board. MBLab to program the PIC microcontroller. Next is block diagram for transmitter section. We have three blocks here: LabVIEW client, Raspberry Pi server, PIC transceiver node. LabVIEW client has a GUI to set the parameters for the transmitter section, and Ethernet port between with the LabVIEW client is connected to the Raspberry Pi server using Ethernet cable. Raspberry Pi server board has a serial communication between the with the PIC transceiver node. It is realized using a USB to serial adapter. PIC transceiver node has a PIC 18F4620 microcontroller to program the RF transceiver module ADF7020. We have a max 3232 as the voltage level converter, and a 2-pin power connector to connect the external battery of 3.3 volt. Next is the block diagram for a receiver section. Here also we have the same PIC transceiver node with the PIC 18F4620 as a microcontroller and ADS7020 as the RF transceiver. We have to program this section using MPLAB, and we have to execute the same section using the MPLAB IDE. Based on the transmitter and the receiver frequency settings, this module can receive the data transmitted by the transceiver node, and the same can be seen in the hyper terminal of the PC using RS232 connector pins. Next is LabVIEW based TCP client. TCP provide communication over single networks or interconnected networks. A client, for the client creation, we have 4 steps. First we have to create a TCP socket with IP address and a port number. Then we have to establish a connection using a protocol like a TCP, UDP or Internet protocol. And communication, we have next is a communication step. The blocks have to communicate each other, that means a client and server communication have to be established. Last one is the close the connection. After the reading and writing operations by the client and server, this function have to be closed. Next is a client formation in the LabVIEW. We have mainly 3 blocks. First one is TCP creation block, which needs an IP address and a port number. Here we are using 127.0.0.1 as the local address and 5000 as the port number. The middle one is the TCP communication block, and any data we have to pass to the server can be passed as the string to the TCP communication block. This block will write the data to the server. After writing the data, the same can be closed using TCP close function, which also has an error handling function. Next is ADS7020 radio transceiver. This has some features and capabilities like frequency bands as 135 MHz to 650 MHz, then 80 MHz to 325 MHz in the divide by 2 mode. Data rate is 0.15 kbps to 200 kbps. Output power is from -16 dBm to +13 dBm. RSSI is 7-bit read byte. Modulation is ASK, FSK, OOK or GFSK. In this project we are using GFSK. Temperature sensor ranges from -40 degrees Celsius to +85 degrees Celsius. Next is the ADS7020 pinout. All the some pins like data clock, data IO, serial clock, serial data, serial latch enable, serial read, interrupt or log, then chip enable have to be interfaced with the PIC microcontroller in the GPIO pins. Next, a data clock is next we are going to see what all are the pins. Data clock is to synchronize the data in receiver mode and latch the data in transmitter mode. Data IO is the transmit data input or receive data output. A serial clock is used to clock the serial data to the register. S data is the serial data input. SLE is the load enable pin. S read is the serial data output. Interrupt or lock is a bidirectional pin. Chip enable to power down or power up the ADS7020 module. Next is ADS70 evaluation software. In this software we have a mode option, PLL, basic features, power down bias current, PA output power, FSK mode, advanced features, and some update registers. In order to we can set different options like crystal frequency, RF channel frequency, transmitter mode, receiver mode, chip enable, then modulation scheme, demodulation type, bandwidth. All the things can be set using this evaluation software, and the registers which is automatically updated in the software itself. So in order to program all those registers and in order to program the parameter settings in the IDF 7020, we can use this evaluation software. And out of these 14 registers, only register 0 to register 6 are programmed registers. Mainly we are using, in this project we have used register 0 and register 2. Register 0 is used to set the frequency parameters, and register 2 is used to set the power levels in the ADF 7020. These are the ADF 70 register 0 values for frequency settings. We have two sections in the project. We have one is transmitter, next is receiver. Both are ADF 7020 transceivers, and in the transmitter side we have selected only 5 frequencies from 433.3.9 megahertz to 433.1 megahertz, and the corresponding ratio 0 values are also listed in this table. In this ADF 7020, it can afford up to 200 kilohertz deviation between the transmitter frequency and the receiver frequency. So we are using 200 kilohertz as the deviation. In the transmitter section, if we are selecting 433.9 as the operating frequency, the receiver frequency should be 433.7. That means 200 kilohertz deviation is possible here. And the corresponding ratio 0 values in the ADF 70 is listed in the table. This is a frequency calculation. Frequency is equal to crystal frequency divided by R into integer n plus fractional n divided by 2 raised to 15. R is the counter value, which is 1 in this transceiver. Crystal frequency is 11.0592 megahertz. And integer n and fractional n can be calculated using this equation, and the register 0 values can also be found using this formula. In register 0, only dB4 to dB18 represent fractional n value, and dB19 to dB26 represent integer n value. Power calculation. Power in dB is given as minus 16 plus 0.45 into power level. Power levels are set using dB9 to dB14 bits in the register 2. Next is Raspberry Pi. It's a cheap computer with a basic level of functionality. In this figure, we can see one Ethernet port with 100 kbps data rate, then 4 USB ports, one HDMI slot, then power connector, which is a micro USB power connector, then SD card slot in below the board, then some GPIO pins are also taken out. For serial communication in Pi, we have to first install minicom in Raspberry Pi using the command sudo apt-get install minicom. After to run the minicom, we have to use the command sudo minicom -b 9600-o-d /div/tty am-a0. B 9600 represent the baud rate, and O-D is a device. In the Raspberry Pi, we have serial communication using USB and also using serial pins. If we are using serial pins, we can TTL pins, then TTY AM-A0 is the device. This is a minicom terminal. We can have a serial communication between two devices, that is between Raspberry Pi and any serial device like a hyper terminal in PC also. What all are the things we are writing in the minicom will be displayed in the. This is a minicom terminal. To have serial communication between the Raspberry Pi and any other device, we can check this serial communication with the PC with the hyper terminal. Next is data packet frame created in the LabVIEW. In LabVIEW, we are setting frequency and power level for the ADF 70. So we have to transmit some corresponding values for the frequency and power variable in the data packet frame together with the message. Frequency parameter is only 1 byte, power variable is only 1 byte, message is of any number of bytes, and carriage return is of 1 byte. Sample frame. If we are taking frequency as 433.1 megahertz, power level as 33, and message as hello, then the packet frame we have created is 1 hello /r. First letter 1 corresponding to the frequency value 433.1 megahertz. If you are choosing 433.3 megahertz, then the number will be 2. If you are selecting 433.5, then the number will be 3. And for power level also, we have selected 3, 33, 63 levels. And if you are selecting third level, then the value will be 0. And for the 33rd level, we are taking that as the first value. And then the message, and then the carriage return. Serial coding in Pi. For serial communication in Pi, we have some functions like serial open to open the serial port in the Raspberry Pi, serial getChar function to receive the data from the device, serial puts to print the data to the other device. Then some commands are GCC. Command for compilation is GCC -o filename.c -l wiring pi. L wiring pi is a header file which includes all the serial communication. Programming the IC, then we are going to run the target. Now in transmitter module, which is already programmed and is powered using 3.3 volt battery, transmitter is connected with the Raspberry Pi using USB to serial converter. Now I am setting the frequency of transmitter as 433.3 megahertz and power level of 33 in LabVIEW. This is the LabVIEW block diagram for power and frequency settings. And I am changing that to 433.3 megahertz, power level of 33, and OK button. And before going to run this application, we have to set the Raspberry Pi. In Raspberry Pi, we have already done a coding for serial and the server communication. Open the terminal. This is Raspberry Pi monitor, which has Raspbian OS already installed. Now we are going to run the program. First of all, we have to go to the desktop. This is a command for running the code. Our code is already saved as server serial 11.c, and the object file we are going to create is server serial 11, and we are using L wiring pi as the header files, and GCC is a compiler. Now we are going to execute that using this command sudo./server serial 11. Then enter. The show socket created, binding has done, and waiting for the incoming connection. Now we have to run the client which is the LabVIEW. We are going to run that. Connection is accepted. In Raspberry Pi we can see that connection is accepted, and in transmitter section we can see that blinking. And in receiver we have received that thing which is indicated by using green LED. In LabVIEW we have set 10 as the iteration number. So after 10 10 iterations it will stop, and the connection will be reset by the peer. That receiver command will be seen in the Raspberry Pi terminal, and communication can be verified using this two LED blinking. In transmitter we have red blinking, and in receiver we have green LED blinking. Thank you. Frame. Next is flowchart for the project. Flowchart for transceiver node. In the transceiver node, we have to initialize all the header files, and we have to initialize the up counter by using timers and registers. Then give the low to high pulse on chip enable to power up the ADF7020. Then set the receiver mode with the frequency value. Then blink a red LED to indicate the device is ready for operation. If the UART will receive the data transmitted, if they receive the transmitted data, then write the corresponding frequency value in the register 0. Then decode the data using Manchester technique. Then calculate CRC and Manchester encoding. Then blink a red LED and send the data. If the data transmission is completed, then enable the RF receive mode, display the same in the hyperterminal, and check the CRC received. If the CRC is matched, then it will blink the green LED. That means the receiver will receive the data and will stop the communication. If the CRC does not match, then it will blink the yellow LED and discard the message. Then it will go to the next upper section C. In the C section, it will again calculate the CRC, and it will do the Manchester encoding, and then it will wait for the next data frame. Then flowchart for the SDR system, software defined radio system. As a whole, the system, it has to configure and program the PIC transmitter node. Then you have to set the parameter values and click send button in the LabVIEW. After connection between the LabVIEW and LabVIEW PC and Raspberry Pi with the Ethernet cable, connect the PIC transmitter with the Raspberry Pi using USB to serial adapter. Then configure, then debug and run the PIC receiver node with PIC2. Compile and execute the server and serial coding. Then it will go for connection accepted. If the connection is accepted, it will run the LabVIEW. We have to run the LabVIEW client section. If it does not, then check the IP address and port number. Then again we have to go for the connection acceptance. Raspberry Pi USB node will write the data to the PIC transmitter serial port. If the PIC transmitter transmits the data and it blinks the red LED for the transmission indication, PIC receiver will receive the data and it will blink the green LED. Then the function will be stopped. Next is simulation. This is the front panel we have created in the LabVIEW. Heading as a parameter settings, or we have selected only two parameters, frequency and power levels, which has a control node. We can upcount or decrement the values using these control nodes, and after setting the we can also write the message here. Here I am giving my name as a message, and after setting the frequency value, we have selected we have set 433.5 megahertz and power level as 633, and after writing all the things, you have to click the send button. Then the other monitoring panels like frequency, packet formed here, power values will display the original value, frequency will display the frequency band, and power value will indicate, power values will indicate the original power in the dBm. And the data packet formed is also being shown here. As we have selected 433.5 megahertz, the corresponding value is 2, and 63 power level, the corresponding value is 2, and the data message is as LG. Then so totally the packet formed is 2 Lg. Next is LabVIEW block diagram. We have to write the register values according to our requirement. Conference and publications. Software-defined radio with Ethernet interface is a paper on the same project in International Journal of Engineering, Science and Innovative Technology. Second one is implementation of biometric sensors based security system. In this paper I proposed a method to implement a gate system using biometric sensors like alcohol sensor and fingerprint sensor, which is published in the proceedings of IEEE Second International Conference on Knowledge Collaboration in Engineering. Auto-comforted wheelchair system for physically challenged paper explained about the control of wheelchair using accelerometer, which is also presented in the proceedings of IEEE Second International Conference on Knowledge Collaboration in Engineering. Next is vehicle density estimation using GPS and ZigBee networks to control traffic signals, which is published in International Journal of Engineering, Research and Technology. References. These are some of the references I have made for the project completion. Then thank you for listening. Thank you everyone.